So today's speaker is Marika Taylor from Amsterdam on black hole deconstruction.
Okay, thanks. So yeah, you're not expected really to know what black hole deconstruction is, although the term has appeared in the literature, but I'll explain it as I go on. So let me start with a little bit of introduction. So it's actually 10 years ago this month that Modasena's paper about the ADS-CFT conjecture came out. And by now, in the last 10 years, we've accumulated a lot of evidence for this conjecture, and also many examples of gravity gauge theory dualities. So in this program, a lot of discussion has been made of, testing the ADS-CFT conjecture. So in the beginning, the tests were made by matching non-renormalized quantities such as protected operators, their correlation functions. And of course, more recently, there's a lot of work on the integrability of the theory at the conformal point in the planar limit. So this is very beautiful work. But of course, we're also using gravity gauge duality in a different way. Many interesting applications of holography come from breaking conformal invariance and going away from the conformal point. So for example, people are trying to use holographic engineering to open a window into gauge theories at strong coupling. For example, another thing which has been discussed a lot in this program is that there are attempts to construct geometries which realize duals of interesting confining gauge theories with chiral symmetry breaking. Moreover, we use black hole geometries to probe the thermal physics of quark-gluon plasmas at strong Toft coupling, thinking about RIC physics and the physics coming up at LHC. Now, in virtually all of these cases, we can't hope to have non-renormalization theorems. We want to extract quantitative, precise results from the geometry because the interesting questions are precisely those which we can't access by any other kind of computation, any other weak coupling computation. Now, on the other side, a separate set of developments, there's been substantial recent progress in classifying supersymmetric geometries. And we have many families of geometries which should be in the framework of gravity gauge theory dualities. They're families of asymptotically ADS geometries, for which one would like to know the dual field theory description. Now, in particular, actually we have, black holes, the supersymmetric black holes that we understand, are definitely within the framework of ADS-CFT. And as with Harvey in the room, one should emphasize this, that there are supersymmetric black rings, and understanding the CFT description of these, more generally other objects, black rings surrounding black holes called black Saturns, this remains an open and important problem. Now let's go back to 10 years ago. So 10 years ago, when we were discussing the microscopic description of black holes, what we did was the following. We took supersymmetric black holes, we gave them mass, the angular momentum, and the charges, and then we took a guess about what the CFT dual was. So in particular, for things like the Strominger-Vafa case or the BMPV black holes in 5 dimensions, this worked unreasonably well. Just giving this small amount of data should not have given us enough information to identify the CFT dual. So it's clear that now we have many more black objects, black rings. We've got to get much more field theory information precisely from the geometry to understand what's going on. Of course, going in the other direction, this is all talking about taking a geometry and extracting gauge theory data. Going in the other direction, I give you gauge theory data. This somehow reconstructs space-time. This is holography. There's a very fundamental question at stake. How is the geometry reconstructed? And in particular, how is global structure such as horizon topology encoded in this data? Well, I'm not going to claim to have too much to say about this question. But in the first part of the talk, I want to discuss progress about, in holographic methods, which is extracting precisely data from geometries. And then, building on this, I want to, talk about the implications of this for black hole physics. And in particular, I'll explain to you what I mean by black hole deconstruction. Okay, so this is going to be based on quite a large number of papers I've written with Kostas Skendaris and some of my students over the last few years. So again, the first half of the talk is about developing holographic methods to extract field theory data from a geometry and vice versa. So there were a set of papers last year where we sort of set up the technology, and a paper this year where we applied it to the LLM solutions as a nice example. And in the second half of the talk about black hole physics and the fuzzball proposal, black hole deconstruction, again, there's a whole set of papers which we wrote on this. Plus, you know, I have a technical paper which I'll refer to later on. We have a paper to appear which is called Deconstructing Black Hole Deconstruction. And we're also writing an invited physics report on the fuzzball proposal. So, you know, these papers constitute about 400 or 500 pages. I just want to give you an overview of you know, what we're doing and why. Okay, so I said that, you know, given a geometry which should have a holographic dual, it's an important problem to, you know, to learn how to extract the field theory data. So, you know, the first question you could say is, what would you like to compute? So let's pose this question in the context of an asymptotically anti-de Sitter cross-compact space geometry. And let's assume we've already identified, you know, the conformal field theory, which is dual to ADS P cross XQ. So in particular, we could be talking about, say, ADS5, something which is asymptotically ADS5 cross S5, something that's asymptotically ADS3 cross S3. Now, if we have such a geometry, an asymptotically ADS-P cross XQ geometry, such a geometry should describe some state in the conformal field theory or a state in a deformation of the original conformal field theory. So logically, what you would first like to deduce is the vacuum structure corresponding to this geometry, namely, you know, the vevs of the operators, you know, the vevs which operators have acquired, and the parameters of the deformations. So if we've explicitly broken conformal invariance, we want to know the deformations that we would make. So now I'm going to talk about how you extract that. Let me make a sort of footnote here, because okay, the technology that I'm going to discuss is very well developed in the framework of asymptotically ADS geometries. Now, this includes many interesting gravity gauge theory dualities, but it's clearly important to go into other cases too, and extend a precise holographic dictionary to such cases. So in particular, again, in this workshop, you know, you would have heard a lot about, you know, trying to set up phenomenological holographic models. So one example would be, say, the Sagai-Sugimoto model, which is a model that has confinement and chiral symmetry breaking. Now, this is based on sort of D4 branes in the bulk, so this is not in the framework of ADS. This is not conformal branes. Similarly, Kalvanov-Strassler is not really conformal either, because it runs logarithmically. You know, the geometry runs logarithmically, and the UV is rather obscure in the field theory. There are also, you know, phenomenological models for holographic QCD, where again the asymptotics are not ADS. Now, in several of these cases, one can actually extend what I'm saying, you know, the precise holographic dictionary to these cases and extract, you know, very precise data. And we have a whole set of papers which are going to come out which are doing this. But, you know, for this talk, I'm just going to stay in the framework of asymptotically anti-de Sitter geometries. But, you know, let me say you can extend it to these cases too. Okay, so again, I said here, you know, firstly, you would like to deduce the vacuum structure for the geometry, vevs and parameters of deformations. Let me give you some examples of this. Suppose we had a dual for an n=1 supersymmetric confining theory. You know, so there are kind of candidate semi-duals. I mean, you know, not entirely satisfactory, but there are some candidates for this. You know, what kind of things would you like to extract? So firstly, again, you might like to extract the deformation parameter that, you know, breaks the supersymmetry down to n=1. You know, you would want to extract, say, the vev of the Cluino condensate. You know, that's in the context of, you know, trying to realize some holographic dual to a QCD-like theory. Now, that's, you know, on one hand, I want to talk about, you know, holographic models for QCD. On the other hand, I want to emphasize, you know, ADS-CFT is also, you know, our best hope of really understanding black hole physics. So let's move to black hole physics. So in the context of black holes, what you would like to do is the following. You would like to extract from their decoupling ADS regions the mass and the angular momenta, or in other words, the vevs of the CFT stress energy tensor and the R currents. Now, I should say that these are not actually necessarily the same thing, or even usually the same thing, as the mass and angular momentum with respect to asymptotically flat infinity. It's very important to remember that the CFT data in black hole geometries is encoded naturally in the asymptotics of the decoupling region, not at flat infinity. And that's what I'll come back to this point later. Now, again, this kind of discussion should talk to people who are doing discussions of black holes, because for people studying black holes, this is often the only CFD data that they give, just the mass and the angular momentum. But actually, there's another, an entire tower of conformal field theory data, which is encapsulated in this geometry. So to illustrate this point, let's go to a simple black hole system. Let's consider the case of the D1, D5 system, which is relevant to, say, black string objects. And the decoupling region in this case is a familiar ADS3 cross S3 cross X4, where this is T4 or K3, won't play a role for me. Now, recall, according to the ADS CFT dictionary, which was set up 10 years ago, the supergravity spectrum of fluctuations about this background corresponds to the chiral primaries of the dual D1, D5 conformal field theory. So lowest dimension operators of this conformal field theory include the stress energy tensor and the R-symmetry currents. But from the Kaluza-Klein excitations on the sphere, one obtains towers of primary operators of increasing dimension. You increase the harmonic on the sphere, and then the dimension of the operator increases. So the vectors of these operators thus characterize the field theory state to which the geometry corresponds. So if I give you the vectors of the stress energy tensor, R-symmetry currents, and all these other chiral primaries, I'm going to get much more information about the holographic dual. Now again, going back 10 years ago to the very famous papers by Witten and Gupsev, Polyakov, Klebanov, the correspondence, how these vectors and deformation parameters was encoded in the geometry, they set up the basic correspondence at this point. The basic idea is that the normalizable modes in the near boundary asymptotics of the bulk fields are related to the vectors. So again, I'm taking this entirely from, say, Witten's paper of 10 years ago. Let's write the ADS metric in the Poincare coordinates so that R equals 0 is the boundary of the space-time. So now if I take a scalar field of mass m squared on this background, I look at behavior of this near the boundary as R goes to 0. The scalar field has, there are two different solutions to the scalar field equation. There's a non-normalizable mode, phi of x, which behaves with this radial scaling, and there's a normalizable mode, phi tilde of x, which has this radial scaling. And the delta that appears here is related to the mass parameter and then the dimension here. So we have ADS d plus 1, and the parameter delta is going to be the dimension of the dual operator, and is related to the mass like this. So then, according to the dictionary of 10 years ago, this non-normalizable mode is related to the source of the dual operator, and the normalizable mode is related to the VEV of the dual operator. So basically, this part of the dictionary was set up 10 years ago. However, actually extracting the VEVs quantitatively from an asymptotically anti-de Sitter cross-X geometry is a lot more subtle. So the point is that this was taking a scalar field on a fixed background. It was looking at the linearized problem. If we have a full solution of the supergravity equations, the relationship reviewed above is a lot more complicated than this. The VEVs are highly nonlinear in the supergravity asymptotics. Now, in some cases, if I just take the geometry and I use this linearized approximation to see, do I have a VEV for this, do I have a source for that, I will get an answer that's qualitatively correct. However, there are equally many known cases where you get qualitatively incorrect answers, things where you know that you can't possibly have the right answer. So for example, you find a non-zero energy for a vacuum that you think is supersymmetric. Or you'll find VEVs for operators which are certainly kinematically prohibited from acquiring them. So we have to do better than this if we want to precisely extract information from a geometry. So this is actually, okay, so of course, this whole, extracting data precisely has been studied, considerably over the last 10 years What we added to this in our paper last year is essentially that we put back in the compact space. We could work with things which were not just asymptotically anti-de Sitter, but we could really extract the VEVs of all the tower of operators associated with the Kaluza-Klein modes. So in particular, what we did was derive holographic formulas for the VEVs in all generality for backgrounds which are asymptotically ADSP cross XQ. So we start from these basic principles of gravity gauge theory duality, relating the bulk fields to the boundary gauge invariant operators, relating the bulk partition function to the generating functional of the boundary correlators. And we got exact formulas that give the VEVs of all the primary operators non-linearly, precisely in terms of the coefficients in the asymptotic expansion of the bulk supergravity fields. So to sketch what I mean, let's suppose we have supergravity fields, symmetric, dilaton, say a 5 form in the case of ADS 5 crosses 5, the other fields of supergravity. We express them as perturbations about the ADSP cross XQ background as delta G, delta phi. Now we expand the perturbations near the boundary as R goes to 0, and expand them again in terms of the harmonics of this space. This is a compact space for all interesting cases. So that schematically you can write each perturbation as a sum over radial expansion, and then Y denotes a harmonic on XQ. Actually, for many interesting cases, of course, this space is actually a sphere, so these are really spherical harmonics. So now the formula that we get express the VEV of any given chiral primary in terms of these coefficients here. So we get exact expressions like this, where what we had to determine was these coefficients, these AM, AJ. And as I said, these are non-linear in the asymptotics. So now one has to say, okay, what's the organizing principle of this? Where do these coefficients come from? And that's what I'm going to explain to you now. So in actually deriving such a formulae, you have to deal with two separate issues. So the first is, essentially how do you deal with infinite volume divergences? So as I'll come to in a moment, the fact that we have, anti-de Sitter is a non-compact space, so we have infinite volume divergences. This, in a sense, is evidence for, okay, it's consistent with the identification with the CFT, because the infinite volume divergences are related to the UV divergences of the conformal field theory. So actually, the fact that we need to regulate and renormalize these divergences, this is related to the renormalization that we would have to do in the conformal field theory. So this I will come to in a moment. We have to take this into account properly. And also we have to, learn how to deal with the compact part of the geometry, because we really want to access the VEVs of all chiral primaries. We don't just want to get those which are captured by gauge supergravity, because that would be restricting us to just the stress energy tensor R symmetry currents. And I said I really wanted all the operators I could. So the first issue is dealt with by holographic renormalization. This is the precise analog of the QFT renormalization and has been studied a great deal. And the second ingredient that was new in our paper is something we called Kaluza-Klein holography, which is really accessing all of these VEVs. Now again, there's a lot of literature on this subject, and our papers are quite long and detailed, and there are many technical subtleties. I just want to give you an overview of the basic principles in this derivation. So if we have, let's just focus first on the asymptotically anti-de Sitter part of the space. So an asymptotically anti-de Sitter space-time is one which solves the Einstein equations with a negative cosmological constant. And near the boundary of the space-time, the conformal boundary, you can always make an asymptotic expansion of this form. So R equals 0 is the boundary, and then this metric can be expanded in powers. It's an expansion in R. And okay, the mathematical result that Pfefferman and Graham showed is that these coefficients in the expansion are related locally to the coefficient G0. And then this term GD is related, this is the normalizable mode, which will be related to the VEV of the stress energy tensor. So this will be the source for the stress energy tensor, and this will be the VEV of the stress energy tensor. So, okay, a covariant way to organize this expansion is in terms of eigenfunctions of scale transformations, again mirroring what one would do in the conformal field theory. So this was the ingredient that came in this paper. And then, you know, the underlying structure of renormalized holographic correlators is best exhibited in a radial Hamiltonian formalism, where we use a Hamiltonian where the radial coordinate plays the role of time. So a fundamental property of these spacetimes is that the scale transformations are part of the asymptotic symmetries, and every covariant quantity can be decomposed into a sum of terms having a definite scaling. So in other words, I mean, in particular what this means is that the radial canonical momentum can be decomposed into eigenfunctions of scale transformations, and each of these is then related to the asymptotic coefficients by nonlinear relations. Now, okay, that's the mathematical statement. Let me give you the meaning of this. I said that my formula for the VEVs of operators were going to be nonlinear in the asymptotic coefficients. The reason they're nonlinear is because the thing that scales properly is the radial canonical momentum. You know, we want the VEV of an operator which scales in a particular way. The thing which, you know, that scales properly is the radial canonical momenta, and this is related nonlinear to asymptotic coefficients. So the meaning of the structure is the following. Okay, the first approaches to doing holographic renormalization were the following. We took the recipe of GKP and Witten, which is, you know, that they said, okay, the on-shell action in the bulk should correspond to the generating functional in the conformal field theory. But both sides were infinite. We have infinite volume divergences. So what people did was the following. You cut off the boundary, so the boundary was at r equals 0. Cut it off at r equals epsilon. Regulate divergences in the on-shell action, add some counter terms, get a finite renormalized action. Then, you know, you treat this as the generating functional for the conformal field theory and obtain your correlators. This results in explicit formulae for the VEVs in terms of the bulk field asymptotics. It's perfectly correct as a method, but it's not utilizing all of the underlying structure, and is thus unsurprisingly not the most efficient method. You have to do a lot of work, and you know, you get expressions for the VEVs which look a mess, and you don't understand, you know, where they came from. So in the new way of doing holographic renormalization, you know, you express the relationship between VEVs and supergravity asymptotics as follows. So this, let O be the set of operators of dimension k, I as a degeneracy label. Then essentially the formulae are just this. You know, they're just expressed neatly in terms of the radial canonical momenta. So there's this term. For most cases, that's just it. You know, that's it. There's one term. The pi is expressed nonlinear in terms of the field asymptotics, but you know how to build the pi because you need the thing that scales properly. Now there's a technical subtlety in some cases that there are also additional terms which arise whenever you can split the k into a sum of k, and that, you know, the constants you get here are related to extremal correlators. I mean, this won't play a role for me. I just make the comment about it. So, you know, these are you know, nice formulas which use all the underlying symmetry structure, and we know how to, you know, how to get from them, you know, the VEVs in terms of the field asymptotics. Now, in particular, this degeneracy label includes the R-symmetry transformation properties, or in other words, the harmonic on the compact space XQ. So, you know, we're not limited anymore to things which are just, you know, the lowest dimension operators. We can really access also, you know, all of the things dual to all of the Kaluza-Klein modes. So that's, you know, in a sense, the progress that we made in this paper. So we have expressions for the one-point functions explicitly in terms of the asymptotics of the 10-dimensional solutions. We have the relationship between the pi and the 10-dimensional field asymptotics. And so if I give you any asymptotically, say, ADS5 cross S5 solution, you know, to get the VEVs of the operators, all you do is just expand it out in the radial coordinate, you know, decomposing the deviations into harmonics, plug them into our holographic one-point functions, get the VEVs. I should say, I mean, again, a slight technical comment. I mean, although in principle we can actually access the VEVs of all dimension operator, computationally, it actually becomes a little bit more, you know, cumbersome to get it for high dimension operators because we have to expand out. We construct the map in a sense perturbatively. So we only have a finite number of fields participating in the computation of the VEV of a given operator, but this number increases with operator dimension. However, that's not a real problem because if we had a terrifically interesting holographic solution, you could just put this on the computer and get out the answer. Okay, so let me make two remarks. So this methodology allows one to extract, using just algebraic manipulations, the QFT data for the one-point functions, for the deformations, from any supergravity solution which is asymptotically ADSP across SQ. This gives you a lot more data that can be used to identify or verify the holographic dual. If I want to get correlators on top of it, I have to do a little bit more than algebraic manipulations. But okay, for the one-point functions and the deformations, just algebraic manipulations. The second comment is the following, that we've derived holographic formulas in generality. You can then apply them to specific solutions. So, in a sense, one doesn't have to go through, for most interesting cases, the formulas have been derived, and you can just plug it in and say, okay, here's the stress energy tensor, here are the R-symmetry currents, here are the VEVs for the other primary operators. Okay, so now let me make a comment here. You could say, is this whole formalism of holographic renormalization really necessary? Because actually it's not used for all holographic computations. So let me make the following comment. Background subtraction works fine for computing just the on-shell action. Now there are some subtleties in doing this, particularly if you have, say, rotating black holes or something like that. But okay, it's sufficient. So, for discussions of things like the phase diagrams of, holographic QCD things as functions of temperature and chemical potential, that works fine. If we want to go beyond this and compute things like VEVs and correlators, doing any kind of naive subtraction infinities, not just rarely but frequently, gives qualitatively incorrect answers. Typically, the answers you get are not consistent with supersymmetry. They're not consistent with the required ward identities. Correlators have unphysical poles, etc., etc. There are many things that go wrong. So, if you really want to do precise computations, you do need to use these techniques. I talked about getting just, VEVs of operators. The same kind of formalism is also needed for discussing non-local operators and corresponding bulk branes and strings. So in particular, I have in mind, Wilson loops, the way that Alde and Modesena are using Wilson loops to describe gluon scattering. Holographic renormalization is implicit in this too, to get the precise answer. Okay, so let me give you some applications and examples. So this kind of methodology allows you to make strong tests of gravity gauge theory duality beyond the conformal point in cases where non-renormalization theorems are applicable. So to give you one example, let's put n equals 4 super Yang mills on the Coulomb branch. So the theory has a Coulomb branch which corresponds to giving a VEV to the 6 scalars of the theory, subject to the condition that they commute. So you can parameterize this Coulomb branch in terms of the VEVs of scalar chiral primary operators. So these are the O's which are built out of symmetric traceless tensors of SO6. That's denoted by C. Now, in the large n limit, a generic point on the Coulomb branch is described by a smooth distribution of eigenvalues for the 6 matrices, and you can compute the VEVs exactly with this result. This is some specific numerical coefficient, and it's computed as an integration of the distribution of eigenvalues. Now these VEVs are known to be protected from quantum corrections. 16 supercharges is enough for this. It's kind of a corollary, well, perhaps you can tell me better, but it is a corollary of Seiberg-Witten's result. So the challenge for holography is to get exactly these VEVs from the corresponding supergravity solution. Now the corresponding supergravity solution corresponds to taking multi-centered D3 brane solutions, take the decoupling limit. So we get this kind of metric where H is the harmonic function but without the 1. We drop the 1 because we're in the decoupling limit. We have, the harmonic function is characterized by the same smooth distribution of D3 branes as the distribution of eigenvalues in the field theory description. So we have this harmonic function. This harmonic function near the boundary of the space can be expanded in this way. So now you see these are the scalar spherical harmonics. This is the radial expansion near the boundary. And then we have specific coefficients. I haven't assumed this. I've assumed, so I have a field theory description and I have a proposed correspondence for the distribution of the D3 branes in the bulk. And I'm assuming that the distribution of D3 branes is indeed the eigenvalue distribution in the field theory. It's the same row of X appearing.
The row of X are the eigenvalues of the gauge group indices of the scalars.
Well, it's so X is a position in SO6, and we have N. Well, okay, we have so essentially the row of X is normalized so that it integrates to N. Okay, so you know I've lost the discreteness in this limit. If that maybe answers. I mean, I can tell you more afterwards. Okay, so we expand out the harmonic function, so we can implicitly. From the expansion of the harmonic function, we can take the expansion of the metric and the other fields near the boundary. We plug into our formulas for the holographic formulas for the VEVs. We get this result, and this precisely agrees with the result from weak coupling. I mean, this over here. So indeed, we reproduce precisely the correct VEVs that we expect, which tests, the proposed correspondence between the multi-center solutions and the Coulomb branch. It's arbitrary. It's arbitrary on both sides. It's for any. So it's sitting in here. This is arbitrary. We do it in all generality. So this is a nice test of gravity gauge theory duality away from the conformal point. There are very few tests actually away from the conformal point. Now we can play the same kind of game with the so-called LLM bubbling solutions. So these are these geometries are meant to be dual to half BPS states of n equals 4 on R cross S3. We get the same impressive ingredient between the gravitational and QFT computations. So this was contained in this paper. So in a sense, you can say this is testing, of course it's testing the gravity gauge theory correspondence, but I mean actually we kind of believe, in these cases we really believe we made the right identification. So we're also testing the methodology. We're testing that, we're computing the VEVs correctly from the geometry. So having tested this methodology and the correspondence, in these cases where non-renormalization theorems apply, you can now move on to extract strong coupling information in other cases, interesting phenomenological models where you don't have the results of weak coupling. Also, one would like to use the same techniques to take, these families of previously known solutions and try and identify or get more information about the field theory duals. So this brings me to the second half of the talk, which is black holes. So as I said at the beginning, I mean, the supersymmetric black holes whose entropy we understand well microscopically are certainly those for which ADS-CFT is applicable. So in particular, the original Strominger-Vafa 5-dimensional static 3-charge black hole, or the BMPV black holes which add angular momentum to the same black hole, are described by the dual 2-dimensional D1, D5 conformal field theory. This is the best, I would say the best understood case of black hole physics. So questions such as, the microscopic description of black rings can certainly be addressed with the tools discussed above. So we have in this case, we have explicit solutions, supergravity solutions for supersymmetric black rings. It's an open question to know how are these described in the conformal field theory. Now, you can use these tools. Okay, I have a paper which is going to appear to say, actually, earlier suggestions are partially right, partially wrong. I'm not going to discuss this anymore. I'm going to move into another idea in black hole physics, which is certainly a far-reaching idea, which is the Fuzzball proposal. So, okay, the Fuzzball proposal, black hole deconstruction, up to certain technicalities are the same thing. I'm using, the words interchangeably. I kind of prefer the first myself. So I'm going to kind of give you a review of what this is, and then tell you what we've done to develop the fuzzball proposal. So the basic idea of the fuzzball proposal is that for any black hole, one can find an exponential number of horizon-free solutions, geometric solutions, that look like the black hole asymptotically, but generically start to differ from it as you go into where the horizon would have been. So in this form, I think this proposal was first made by Luhn and Mazur in 2001, with the evidence that I'll review a little bit later. So the idea is that each of these horizon-free solutions should represent a microstate of the black hole, and the original black hole is providing only an average description of the system. Now, if this were correct, actually this proposal certainly has the potential to resolve a lot of long-standing puzzles in black hole physics, such as information loss, because you've reduced the physics of the black hole to something which is not really conceptually different from that of a star. Temperature and entropy should now come out from a statistical origin. At the same time, this proposal has not been pushed so much because there's very little evidence for it. Now, we pointed out in one of our papers last year, ADS-CFT actually, the ADS-CFT correspondence not only really supports this picture, but actually says that some form of it should be true, at least for the supersymmetric black holes which are described in the framework of ADS-CFT. We can't, of course, in ADS-CFT say things about general black holes. So more precisely, gravity gauge theory duality wants to relate an asymptotically anti-de Sitter geometry to either a deformation of the conformal field theory or the conformal field theory in a non-trivial vacuum characterized by verbs of operators. Conversely, one is assuming in many contexts, if you believe in ADS-CFT, any stable state of the conformal field theory, for any stable state, there is an asymptotically anti-de Sitter solution whose asymptotics encodes the verbs of the operators in this state. So if we put the field theory in a pure state, we have no entropy, and you don't expect to have a geometry with a horizon. It should be horizonless. This is basically what the fuzzball proposal is saying. This should be true. There is, however, no guarantee that the geometry should be well described by supergravity, i.e. weakly curved everywhere. So ADS-CFT, in its full extent, it says that for any state of the CFT, I should have a geometric dual. It doesn't have to be well described by supergravity without the other alpha primed and loop corrections. So, there's no guarantee of this and no criterion for when this holds. By the way, one should also make a comment here that ADS-CFT makes it, a lot less surprising. If you start from this perspective, it's a lot less surprising that there's a plethora of different black objects. Because if I put the field theory in a mixed state, I expect to get an object with a horizon. But clearly there are many choices of mixed states. It's hardly surprising there's a variety of black objects that you can find. In a sense, 4 dimensions is very special, not the other way around. So now let's try and push the fuzzball scenario a little bit further. So the basic, most elementary questions you can ask is, can you find enough such geometries for a given black hole? What properties should the geometries have to be associated with black hole microstates? Can you show quantitatively how black hole properties emerge on coarse graining? Now again, I'm not going to attempt to address all these questions in generality, but people who are trying to sort of push this proposal are trying as a first step to understand the simplest possible cases, which is in the framework of the D1, D5 case. So 2 charged D1, D5 black holes, 3 charged D1, D5 black holes with some momentum on the brains as well. So these were the cases, or this in particular, this is the Strominger-Vafa case, where we actually first understood the entropy, we have the most control over the CFT, we have supersymmetry. Of course, in the case of, where we have supersymmetry, we're never going to see things about how does temperature emerge, but this is a good first step. So let's start from the easiest case of all. So if we start with the D1, D5 case, so we have, the D1, D5 case, recall, is a case where we have, there's a degeneracy of the ground state in the conformal field theory. I mean, one is counting, the degeneracy of the Ramond ground states. We have an entropy, but it's not sufficient that the system in supergravity acquires a horizon. It's a so-called small black hole which only gets a horizon after alpha prime corrections. However, there is a very large entropy of this system which scales with the number of D1 and D5 branes. So, let's consider this case first. Now, the simplicity of this case comes from the fact that you can do dualities and take it back to fundamental strings carrying momentum. And it turns out that in the literature, supergravity solutions describing fundamental strings with arbitrary momentum profile were known for really a long time, more than 10 years ago. So in fact, they're actually chiral null models where the 10-dimensional metric looks like this. It's characterized by three functions, h, k, and the am are also harmonic functions, plus there's a dilaton, and then there's a b which actually matches this term. So this is a chiral null model. It's characterized by harmonic functions which are sourced on arbitrary curves, arbitrary null curves, and these curves describe the profile of the string. So I can choose an arbitrary profile of the string and I get a different supergravity solution. So I have families of different supergravity solutions. Now, okay, as I say, it's also known for a very long time that the fundamental string system carrying momentum, we do chains of S and T dualities as usual in string theory, and we can bring this to the D1, D5 system. Now, what the progress that Lun and Merther made 6 years ago was that they basically realized, hey, we can do this, and we're going to get new geometries in the D1, D5 system, which looked like they could be candidate black hole microstates. What we did in our recent paper was get really the most general such solutions by dualizing these geometries. So, if you want to put the D1, D5 system on the torus, you essentially relate this back to the fundamental string system on a torus, and you do S and T dualities. If you want to get the case on K3, this is a little bit harder work actually, because you have to get it from the heterotic string. So then you've got to relate the heterotic string to the type 2 string K3 by string-string duality and use S and T dualities. Why people had not done this before is because not all of the steps had really been put together. I mean, we knew how, working with supergravity solutions, people knew in principle how to do it, but they hadn't really worked out the computational details for, more general supergravity solutions. Okay, so all the solutions you get are characterized by curves. Remember, in the original system, we have a curve, arbitrary curves describing the transverse profile of the string. So now, the solutions in the D1, D5 frame are also going to be characterized by curves. In the K3 case, the curve sits in 24-dimensional space. Now, the reason it's 24-dimensional is because that came from the heterotic string. So the heterotic string had not just the profile in its transverse 8 dimensions, but it also has charge waves as well. For the T4 solutions, we get a curve in 8-dimensional space. Actually, this is not, strictly speaking, the most general solution, because there are also more complicated solutions I found a couple of years ago associated to the branes having fermionic condensates on them rather than just transverse bosonic excitations. But in any case, we have families of solutions which are characterized by arbitrary curves. Now, all of the fields are highly non-trivial in these solutions. So let me just flash the next transparency. You can see it's a complete and utter mess. We went from something which looked pretty simple. We did all this chain of dualities. We got a mess. But it's characterized in terms of harmonic functions, which in turn are sourced on curves. So now I've split up the curves into a curve in 4-dimensional space and then an internal, what I want to call an internal curve. So, these functions F5, A, which appear in the solution, they just look, they're just sourced on these curves. Now, back in 2001, Lun and Merther found a subset of these solutions which just had the curve Fi in the transverse 4-dimensional space. So these kind of represented cases where the D1, D5 branes have kind of blown up into a sort of supertube in the transverse R4. What our solutions are describing, they have these extra curves. They're sort of like, the branes are carrying internal excitations on the compact directions that the D5 is wrapping. So that's, that's the physical interpretation. okay, so, you know, we have these solutions, and you can say, well, okay, let's try and, you know, push the fuzzball proposal and see, you know, do they have the right properties to correspond to, you know, the thing we think they should be, you know, the D1, D5, two-charged black hole microstates, which are the Ramond-Ramond ground states in the dual conformal field theory. So, you know, at first sight, they certainly have possibly that, you know, they have the right properties. They have the same mass and conserved charges at flat infinity as a naive system. The solutions are also non-singular and horizon-free in general. There's a technical condition that this defining curve of the profile can't self-intersect. But they have, you know, these two properties. Note that in general we have non-zero angular momentum, and we also have a lot of multiple moments, you know, measured with respect to flat infinity. So as I said before, the curves Fi, this is the curve in R4, that's a transverse excitation. That's the blow-up of the branes in R4. The F and the other curves are excitations in the internal manifold. Now it actually turns out that if the blow-up is 0, the solution collapses to just a naive solution. I can't switch on the internal excitations unless I've also blown up the curve, which I'll explain a little bit later why that is. Now, okay, prior to our work, pretty much the only evidence for these solutions to be related to the two-charged black hole microstates was what I said before. They have the correct charges, they have no horizons. However, you know, you can use the fact that in the decoupling limit, all the solutions emit an asymptotically ADS3, antidissociative 3 cross S3 cross T4 or K3 region. So you can use the holographic methods I discussed in the early part of the talk to probe what the field theory dual is. So the infinite amount of other CFT data, namely the vevs of the chiral primary operators, encoded in this geometry, are the very precise way in which the field theory knows about the multiple moments at flat infinity. As I said at the beginning, you have to go into the decoupling region to, you know, to extract the CFT data. Okay, now, like I did in the case of the n equals 4 Coulomb branch, I have harmonic functions which characterize the solution. These are very naturally expanded near the ADS boundary in terms of spherical harmonics. So I take this function F5, this is expanded in terms of a spherical harmonic, and then the radial power, and then I have a specific coefficients which are related again to, you know, the curves on which the solution, the harmonic functions are sourced. So, you know, one gets this kind of expression. And I have expressions for the vevs in terms of the field asymptotics. So I just plug, you know, the expansions into the expressions for the vevs to get them in terms of these integrals. So when I do this, I find the following. Firstly, I mean, it's actually non-trivial to show that the vev of the stress energy tensor is precisely 0. Now, it's a very non-trivial calculation. It comes out like this. And this is in precise agreement with the fact that the fuzzballs are conjectured to be dual to Ramond ground states in the conformal field theory. We have the right mass. Furthermore, we get non-zero vevs for the R symmetry currents. That was the angular momentum in the bulk. And also for the towers of scalar chiral primaries. So schematically, you know, we have this tower of scalar operators which require a vev. And these vevs are given in terms of the integration of the curve over the profile. So again, analogously to what I had in the Coulomb branch. So as I've been emphasizing, there's a lot more data in the geometry than just the charges. So the charges I would call, you know, the stress energy tensor, the R symmetry currents. There's all of this data. And any proposal I make for the holographic dual has to be consistent with all of these vevs. Now let me come to what the field theory, a little bit more about what the field theory dual is in this case. So we have a two-dimensional CFT, which is a deformation of a sigma model whose target space is a symmetric overfold of T4 or K3. The holographic results we got actually immediately invalidated earlier suggestions that, you know, map each of the geometries to a single Ramond ground state. So we proposed a precise map that instead associated a given supergravity solution to a specific superposition of these Ramond ground states. And the exact form of the superposition is determined by the curves which determine the solution. So in other words, if I give you a curve, now the index I is over all the dimensions of the curve, I pull out the Fourier coefficients. I consider a coherent state which contains Fock states. So I expand the curve into Fourier coefficients. I consider a coherent state, and I project it down onto Fock states. And then I map, I map the coefficients of this. These, essentially fundamental string oscillators, to the CFT or Mond operators via precise dictionary. So these are the operators of the Oberfold CFT. I'm using Oberfold language, but these are operators of the D1, D5 CFT, which I can label essentially by the cohomology of T4 or K3 and by a twist label. All that matters for me is I have a precise dictionary between the Fourier coefficients of the curve and the CFT operators. So this allows me to make an identification of, given the curve, what superposition should this be dual to. Now I can take the vevs of the gauge invariant operators. I can compare, the field theory computation with the gravity computation, and I get exact agreement. So I'm only building things out of primaries, so this is known, and it's also known. It's also
BPS or.
So this is I'm talking only about the Ramond ground states, so they're BPS. Yeah. No, sorry.
Same as in the symmetric products.
Yes, it's known. Okay, so it's certainly. Okay, as I'm about to say, it's actually stronger than this. So, it's known, of course, that the spectrum of chiral primaries the spectrum of chiral primaries computed in the Oberfold CFT certainly agrees with the supergravity computation. That's been known for many years. In the last year or so, Atish Deb-Holkar and others, and also my work, have actually shown something stronger than that, which is that there's the chiral ring of is also protected. It's okay. There are a lot of subtleties, but it actually turns out that the chiral ring is protected, which is somewhat surprising because you wouldn't think. The Oberfold CFT is it's an infinite marginal deformation of the CFT we're interested in, but it actually turns out that the fact you have 16 supercharges again enough to protect the chiral ring. So indeed, there are actually non-renormalization theorems for the chiral ring, that's the 3-point functions, which in turn implies that there are actually non-renormalizations for the vevs, in effect. So indeed, I can actually use the calculation in the Oberfold CFT and compare it with the gravity computation. And indeed, this agrees exactly within the approximations used. So approximations used means effectively large n. So I'm dropping things which are subleading in large n. So this is a very strong test of the fuzzball proposal, at least in this case. So it is evidence for the fuzzball proposal, but now let me come to, the subtleties of this. So I said, that ADS-CFT tells you that if I put the field theory in a stable pure state, I should have a geometric dual. But I said it also didn't guarantee that this was going to be a supergravity geometry, i.e., something well described in supergravity. Now in this system, it's certainly true that you have to go beyond supergravity to accurately describe the system. So most of the geometries contain small regions of high curvature, so they're not really well described by supergravity. You can find special superpositions of special choices of superpositions of microstates for which the supergravity solutions, smooth and weakly curved everywhere, but that's not generic. And in fact, when you include geometries with only internal excitation, so this was the case where the D1, D5 branes hadn't blown up at all in R4. This was worse, remember, in gravity because they just collapsed to the naive singular geometry. So these kind of things, according to the map, should account for a finite fraction of the black hole entropy, but they're not visible in supergravity at all. Now, even the geometries that only involve macroscopic scales can only be resolved from each other by effects beyond supergravity, i.e., the vevs differ from each other by a very small amount of order 1 over n. So capital N here is, say, n1, n5. This is the parameter that we're always taking large in its correspondence. So yeah, I mean, many of the geometries have small regions of high curvature, or they collapse to the naive geometry. Other ones can't be distinguished. That's the basic problem. Now, you could say this is, when you think about it for a moment, that maybe this is not so surprising, because remember, the two-charged black hole does not have a horizon in supergravity. It's a small black hole. So if we had managed to find all of its microstates, being macroscopically large, there would have been a contradiction, because when we averaged over them, we should have got a macroscopic horizon. So that's, this is not so surprising. However, the point is you can argue on rather general grounds that these issues are going to persist even in cases like, say, 3-charged, 4-charged black holes which do have horizons in supergravity. So I can give you, we made the argument a lot more precise in some of our papers, but I can give you the gist of it very easily. The point is that the entire interior region of the supergravity solution is reconstructible from the field theory data of the VEVs of the chiral primaries. But if you take this D1, D5 system, add another charge, momentum, so we get a macroscopic horizon, you can see that the VEVs of these microstates are typically very similar to each other. Large numbers of such states will be indistinguishable at leading order in N. And this means that they are indistinguishable as supergravity solutions. So this problem certainly, has to persist for this case too. At best, you could probably only find a representative basis in supergravity. So what this would mean is that you'd find horizon-free, non-singular geometries which are distinguishable, but then to each geometry you'd assign a measure which kind of counts the number of ones which are indistinguishable in supergravity. And if I gave you such a basis, you could envisage coarse graining over the geometries, to get black hole properties, which is, of course, the main objective of this proposal. And moreover, if you did different coarse grainings, you should get different black objects, black rings, black Saturns, whatever. Okay, so now let me move to the status of the systems which do have microscopic horizons. So there has been a lot of work in the last few years in trying to construct geometries for candidate geometries for black hole systems in 4 and 5 dimensions, systems which do have microscopic horizons. Now there's no neat kind of trick that you can use in this case to map it back to the fundamental string or something where you already knew the solution. So basically what people are doing is taking the classifications of supergravity geometries and then looking for particular ansatzes on it to find solutions. So in particular, Benner and Warner have done a lot of work on this. Deneff's work on this subject, he was also looking for things with horizons, but his papers go back about 7 years, and they're also relevant for the 4-dimensional solutions, and also his long recent papers with Moore touching on this subject. So they find some, Benner and Warner in particular claim to have what they call bubbling geometries, which are non-singular horizon-free geometries, have the correct charges to correspond to black hole microstates. But I have to say, this in itself is really not a strong test, because there are completely unrelated conformal field theory configurations. This conformal field theory does have a Coulomb branch, which is completely unrelated to the black hole physics. And I can find configurations which have these same charges. This is not a good test. So to verify whether the geometries are indeed dual to the black hole microstates you hope they are, you would try and extract much more information from the data, extract the VEVs, set up a precise dictionary, as we did in the 2-charged case.
Question?
Yeah.
When you say they've got the correct charges to correspond to black hole microstates, do you mean they have numerically actually the same charges as a black hole? No, the right kinds of charges?
I actually mean that when I extract the holographically, I extract the stress energy tensor and I extract the R symmetry charges, the angular momentum, that those agree with what they should be. I'm insisting on those charges, the conserved charges, the stress energy tensor and the R symmetry charges. That's
they agree with charges in known black holes.
so they would agree with, okay, so their solutions, okay, take Benner and Warner's, put it in the framework of the D1, D5 system. Actually, they usually discuss it in M theory, but put it in D1, D5P. There is, of course, the D1, D5P microstates that Strominger and Vafa were counting, BMPV Vafa. There is a precise proposal for what their what their geometries are meant to describe. So those geometries are meant to describe, those particular states in the CFT.
So I wasn't convinced that their charges actually lay in the same region of parameter space as black holes' regular horizons.
Well, okay, that was true of the older solutions. I mean, the more recent solutions, they claim to have fixed that problem, but wait for the next transparency because it's worse than this. Okay, so we started a couple of months ago with the new solutions, which are meant to lie in the interesting region of parameter space. We tried to set up a precise dictionary, but our tentative conclusion is that these geometries are not really the right ones. I mean, they seem to be illegal in a lot of different ways. The supersymmetry is actually illegal because the killing spinors have cusps as they cross between the regions of different signature in the base space. The killing spinors are certainly sick. They have negative energy sources when I do dualities and take them into dual frames. So I don't have sources in the D1, D5 frame, but if I move it into a frame where I have sources, fundamental string frames, these have negative energy sources. This is not legal. The fractionalization of the charges implicit in the geometries, it doesn't agree with that in the CFT, and it also seems to be illegal and inconsistent. So, okay, at this point, it's a tentative conclusion, but we think that these geometries are not really valid, and that one would have to go back, to the drawing board. I mean, they've pushed this various ways, yeah.
Sorry, could you repeat what you said? They are, in one frame, they're just smooth black hole solutions with no sources. In another?
Okay, so if you want to look for something which is illegal, so if I take, okay, so let's go back to D1, D5. So the D1, D5 solutions don't have, so I have harmonic functions, but there are no sources in the stress energy tensor. I mean, this is the claim of Duff and others, we can verify. But if I pull it back to the F1P system, I do have sources. If I do dualities, I have sources, and that was what Callan and Atish Holker and others were matching to sources, 10 years ago. Now, if those sources become negative energy, negative tension sources, I claim that's sick. And, if that happens, you should reject them as solutions.
It's surprising because the original solution has fine.
Okay, but what they've done is definitely very weird. I mean, if you look at these solutions, so they take in the supersymmetric classifications, they take the hyperkähler space, base space, and then they fiber over it, and they take it. They allow themselves to use hyperkähler base spaces, which change signature. I mean, what they do, they're very non-standard, these solutions, and this change in signature also seems to be to cause the killing spinors to have cusps, which you also think is illegal according to papers you've written. So, I mean, I don't like any of these arguments actually. I think there's a much better way to kill these solutions, but I mean, I'm still looking for this. But I truly think there's something very sick with them, and that they're not the things which are describing the microstates.
Can I just ask about these killing spinors and stuff? So there's this picture of supersymmetric solutions in terms of vibration over a base space. That's just a local picture.
Mm-hmm.
So, but presumably they claim that their solutions are perfectly regular in, say, 5 dimensions.
Yeah. So, well, okay.
If they're analytic, then I'd thought that the killing spinors would have to extend smoothly because the solution's analytic. The killing spinors analytic, which should extend in 5 dimensions. Even though it doesn't look nice on this projection of the 4-dimensional base space, it's just an artifact of that projection.
No, but I mean, the statement I'm making about killing spinors was the 11-dimensional spinors, the 10-dimensional spinors.
So their solution.
I mean, the fact is that it wasn't actually checked systematically.
Right,
I mean,
so their solution is probably not analytic.
I don't think they're analytic, and that's why I say I think I can find a much better way to kill this, because I agree, if they have cusps, there's something non-analytic going on. But this was just never checked. I mean, it was really, yeah. Okay, so okay, we tend to think these things are invalid, and so you have to go back one step and try and find the correct geometries. As I said several times, ADS-CFT requires that such a dual exists. Actually, we kind of have partial results on finding some of the geometries, which look a lot more sensible. But okay, this remains to be done. So that's that's in a sense the summary of that. So let me give you a summary of what we've done with black hole deconstruction. So the fact that we consistently could construct a map between the horizon-free solutions and the microstates in D1, D5, consistent with ADS-CFT, checking the verbs, is a stringent test of the fuzzball proposal. However, for this system, you had to go beyond the leading supergravity approximation to extract the physics. We argue, we have various arguments that this is going to be a problem that persists in other systems, even those with macroscopic horizons. It's likely that you can't actually get the geometries, all of them in supergravity. We don't exclude that you could get a representative basis. If you want to make progress in supergravity, you should try and get a representative basis. And then again, you need all kind of methods or some equivalent to understand quantitatively how typical is a state associated with a given fuzzball solution. So I said you had to put a measure on it. You need to know how typical it is to put a measure on it. And you need to know the precise map between geometries and states. So this is known in the two-charge system. We could actually go through to cost graining, but we know it's not really going to give us anything consistent in supergravity, so we're not doing it there. We're moving, we're trying to do the cases which are, have a hope of giving us something sensible on cost graining in supergravity. Okay, so now let me move to conclusions. So, holography, as is apparent in many of the talks in this program, it can increasingly be promoted to a very precise framework in which we can compute field theory properties from geometry and vice versa. At the beginning I discussed how you decode the hologram for asymptotically ADS cross X geometries. We're also developing the same kind of precision holography for other gravity gauge theory dualities, in the hope that these tools can be used to extract detailed information from phenomenological models, holographic models, and moreover, may help us to understand black hole physics. Now, ADS-CFT implies that some form of the fuzzball proposal certainly holds. The holographic techniques can be used to scrutinize and further develop this proposal. Our results support the picture, although it's actually a lot more complicated than people previously thought. Work is in progress by us and other people, to understand the supersymmetric systems which have macroscopic horizons, are then hence one step closer to the physical black holes. Counter geometries might not be the right one. Okay, we also have this idea that we can actually, use this inversion of the field theory data to construct them. Again, we only have partial results on that. But, it actually seems tractable that, we may be able to, really construct a representative basis for these cases, and see whether the fuzzball proposal is, it holds. Okay, I stop there.
Yeah, if I understand correctly, these dual geometries have continuous parameters, right? Like the curve
Sure.
you introduce, right? So at some point, if you're going to relate that to the microstates of a black hole, you have to replace that continuum by some discrete set of states, by
Sure.
some kind of quantization. That would be required to test the proposal, right? So.
Well, okay, of course, in the large n limit, it's like, okay, in the Coulomb branch, of course that's discrete, but at infinite n. Sorry, the Coulomb branch, in terms of, we have n eigenvalues. I was representing it by a continuous distribution, yeah? So, okay, so if I want to see finite n effects, I definitely have to make that, distribution of eigenvalues must be discrete. I start seeing that. And I would have to do the same quantization
I'm
in the
referring to something
geometry.
quite different. The fact that the eigenvalues themselves are continuous variables.
Yes.
The set of states you're describing is a continuum, right?
Sure, but it is analogous because actually, the continuity of the curve is actually from taking n to infinity. That's what I'm saying. So the continuity of the curve really, really came from that. It becomes discrete if you take, n finite. You're absolutely right. For at least some of the discussions, I would have to do some kind of geometric quantization, on the solutions. And okay, people have explored that. For, the tests I'm making at this point, I'm testing the VEVs at leading order in capital N as n goes to infinity, and the difference between something which is discrete and continuous I don't see, and it's exactly analogous to say, the Coulomb branch discussion. But, of course, you're right. Given the map, you can also think of, say, pushing across the field theory measure onto the geometries to quantize it that way. And you can also quantize it directly geometrically. But, of course, that has to be done too. But in a sense, that's one step ahead. you first of all want to check whether the geometries you have are reasonable and whether, the approximate dictionary you have is, or the dictionary you have is reasonable. That was not correct before our work. That has to be done next. You could also equally ask, of course, if the ultimate hope is to do, say, coarse graining on these geometries, again, I have to coarse grain over a discrete set. I have to do this quantization. I have to tell you how I'm going to do the coarse graining. Okay, that's to be done. So.
I believe that the Fuzzball proposal could be true for far from supersymmetric black holes.
Well, it depends how you define the Fuzzball proposal, actually.
No one defines it precisely enough.
Hmm?
No one defines it precisely enough.
Well, yeah. I mean,
It's very hard to pin people down.
well, okay. I mean, I'm not making judgments one way or the other. I mean, I can give you the heuristic back of the envelope discussions why people don't want it to be true for the non-supersymmetric case. I mean, the highly non-supersymmetric case. I mean, okay, if you believe in gravity gauge theory dualities at all, and you think they're going to hold very much more generally, the fact that the black hole. Okay, so think of the picture of many years ago where we thought about string states. We had a large multitude of string states. We crank up the coupling. At some point, we get a black hole. But if you keep things in a pure state, you wouldn't expect to have a horizon. It's very reasonable in all of these cases that this persists and it shouldn't care about supersymmetry. So, in this sense, that there's some geometric dual, in quotation marks, that doesn't have a horizon, and that coarse graining gives you a black hole, I can believe. If this is, if, however, this is a very stringy geometry, where, the notion of geometry doesn't really make sense, it's highly curved, it's a string background, then I'm not sure this is a useful picture. So, okay, I'm basically neutral, but I don't see ideologically the difference between it being, near extremal and very non-extremal. I just know I can't do anything quantitative in the case non-extremal to test it one way or
I was
not.
just thinking about the real world. What happens if I do gravitational collapse of a pure state in a black hole? If there are these classical geometries that are supposed to describe the microstate, for example, if it's
Well, okay, but that's why I want to take out the word classical, don't I? I don't want it to be classical. I want to allow regions of quite strong curvature, so it ceases to be well described by classical geometry. And of course, as you know yourself, I mean, it's also, people tend to sort of, use. People say, okay, if I take initial data, it generically collapses to a black hole. But actually, the more scalar fields I put in, suppose I take Einstein gravity in 4 dimensions and lots of scalar fields, it's actually quite easy to set up initial data which doesn't collapse to form a black hole. That's not difficult. Now, all of these solutions use crucially the fact that we've got lots of other fields in the game. When I describe them in 4 or 5 dimensional language, I've got lots and lots of scalar fields switched on. So, okay, it's not, there's no contradiction between existing results. It's not, it's not impossible.
The most interesting thing about the program, I think, is what it would have to say about real world black holes.
Sure, yeah.
And certainly we can set up initial data that will undergo gravitational collapse.
Okay, but you could too. You could here too, because I'm emphasizing the fact, if I put, the field theory in a mixed state, I get an object with a horizon. I mean,
No, I would set up a pure state that undergoes gravitation.
Well, okay, but okay, I believe in unitarity, and I don't believe in information loss. I think if you honestly did the problem, taking into account, a pure state will go to a pure state. It won't be necessarily well described in Einstein's theory. You need to really take into account, have a string background. But I don't think a string, a pure state collapses to form a mixed state. So.
Yeah, but you're assuming then that if something has a horizon, that necessarily is a mixed state, which it's not.
Absolutely.
Yeah.
No, that's why I say I think this is of course a statement that ceases to make sense when you don't have a good geometric description. I mean, yeah, that's why. That's why I asked you at the beginning, what do you mean by the Fuzzball proposal?
You do have a geometric description.
I mean, if you ask me to say, do I believe what Mazur is saying? No, because he emphasizes that these are all found in gravity, and I think I've made very clear that they're really not. Do I agree with what Banner and Warner say? Also not. But okay. Do I believe that there's some kind of you know, in these frameworks with supersymmetry, that there is a geometric dual for every, you know, pure state of the CFT. Yes, I do believe this. I mean, I think the evidence for ADS CFT is very strong, and it will persist in those cases. I think supersymmetric black holes will be described in this way. So.
Any more? Okay, let's thank Marika again.